In the last video, I laid out the fundamental definitions and relationships for the vectors position, velocity, and acceleration. These relationships we showed can be written in both differential and integral form. In this video, we will show how these are used to solve problems. This is a typical looking kinematics question. We are given an object's velocity as a function of time, which is true for the domain where time is greater than or equal to 0. This means if we wanted to know the object's velocity at any time greater than 0, we simply put the time, t, into this function and out comes the velocity. Remember, velocity is a vector, an arrow. If the number we get for the velocity is positive, it means the velocity arrow is pointing in the forwards x direction, whilst negative means backwards. The number we get gives us the size of the arrow. Notice we are given one piece of additional information, which we expect to come in handy. Part A asks us to find the acceleration after 3 seconds. First, we want to obtain a general expression for the object's acceleration, and we get that using this relationship between the velocity, which we know, and the acceleration, which we want. So we must differentiate, and doing so gives us this expression. Notice this will also apply for any time greater than or equal to 0. Now we have the general expression, we can find out the acceleration at any time in the domain. We find it after 3 seconds by subbing t is equal to 3 into the function, and we get that the acceleration at this time is 4 meters per second squared. Part B refers to the position of the object, and so we search for a general expression for the object's position. The position is related to the velocity with this relationship, and so we must integrate. When we integrate the velocity function, we get this expression, not forgetting the very important unknown constant at the end. To find out what this constant is, we must evaluate this position function at a time where we know its position. This information has been provided to us here. We are told that after 3 seconds, the object passes through the origin. Subbing in that when t is equal to 3, the object is at the origin, and so r is equal to 0, we deduce that c must be positive 72. Now we have a general expression for the object's position, again valid for positive times. We can address the question. We want to know the object's position when it is at rest. When is the object at rest? Well, the object is at rest when the velocity is 0. And so we set v is equal to 0 and see what times this corresponds to. We therefore need to solve this equation. And factorizing shows us that the solution is when t is equal to 6 or negative 4. Now the function is only valid for positive times, and so we deduce that the object is at rest when t is equal to 6. The object's position when t is equal to 6 is simply found by plugging t is equal to 6 into the position function. And when we do so, we get that the position vector is negative 36. This means that the object is 36 meters from the origin in the negative x direction. Since the question is only interested in the distance and not the direction, we give the final answer of 36 meters. Finally, we are asked to find when the object passes through the origin again. In other words, we need to find when the object's position is 0, and so we are trying to solve the following equation. To solve this equation, we are first going to multiply everything by 3 to make it a little bit nicer. We will then exploit the fact that we know one solution to this equation already. We know that when time t is equal to 3, the position is 0. This means that the left-hand side can be written as t minus 3 multiplied by something else, since inputting t is equal to 3 is guaranteed to make the whole thing equal to 0. We find out what this something is by inspection. We need a t cubed as the highest power of t, so this first term must be a t squared. Now so far, if we multiplied out these brackets, we would have a t cubed and a negative 3t squared, both of which we want. So the next thing we need to address is getting a negative 72t. And to do that, we put in a minus 72, which will give us a negative 72t when we multiply it by the t. When we multiply the negative 72 by the negative 3, we get the 216 that we want. Now the equation has been factorized, we quickly see that the other solutions occur when t squared is equal to 72, giving that t must be positive or negative 8.49 seconds. Again, the function is only valid for positive times, and so we conclude that the object is next at the origin when t is equal to 8.49 seconds.